Hello, ladies and gentlemen. Today we will be covering the final section of electromagnetic induction, which focuses on electromagnetic waves, which is essentially just light. Okay, so this last section focuses on light. Okay, so that's what EM waves are. EM waves are light, and you have different types of light, and they fall into different categories. Many of which you have heard of already. So technically, radio waves, microwaves, infrared waves, the visible ultraviolet X rays, all these things are considered to be light. Okay, so they all fall under the category of the electromagnetic spectrum. And you may or may not have heard that term before in your previous science classes. It is something that's discussed in chemistry. So you may have heard this term before, but just know that EM waves all fall under light. The reason they're called electromagnetic waves is because all of these waves of light have both electric fields and magnetic fields. They just vary a little different based off of the energy that each wave may have. Okay, so EM waves are produced by accelerating charged particles. Basically, if a particle is charged and it is in motion, it can release energy, and that energy can be light. And depending on how much energy it has, that's what determines the type of light that you get. The more energy you have, you may get something like the X rays or the gamma rays. If you have less energy, you might get something like the radio waves or the microwaves, which are a little weaker. Since all EM waves are lights, technically all EM waves travel at the speed of light. Okay, all EM waves travel at the speed of light. So that's a big highlight. Okay. Now, I want to go over the important points. I'm not going to focus on too many little things. I'm going to highlight the things that you should know. Okay. So there's this thing called wave particle duality. That's what they call it here. To summarize that, what they're saying is that light can behave both as a wave and as a particle. What does it mean to behave as a wave? If something behaves as a wave, what that means is that it has the ability to bend around corners. Okay. So, for example, if you're talking in a room and somebody is around the corner on the outside of the door, even though you might not be able to see them, they can still hear you because sound is a wave and it can bend around corners. Okay, light can also do that, and depending on which type you get determines just how good it is at doing that. So this is saying high energy waves behave more like particles. Okay, so the more energy you have, the more like a particle you behave. Okay, and below we have a spectrum. The higher energy stuff is on the right. Okay, so the further to the right you go, that means more energy. So the things to the right behave more like a particle, which is a good thing, and we'll get why in a second. Okay. So going to the right, you have more energy and you behave more like a particle. If you behave like a particle, what that means is you travel more in a straight line and you won't really bend, you'll bounce. Okay. So think of this like a ball. Okay. You can only throw a ball in a straight path. It only goes in a straight direction. It can't really bend around corners and things like that. Once it hits something, it's going to collide with it and bounce. It's not going to bend around it. It's not going to absorb it and things like that. So that's what it means to behave like a particle. So this wave particle duality, to summarize, it means that the more energy you have, the more you behave like a solid object that's going to collide with something and bounce. The more like a wave you are, the more rubbery or stringy you are, where you can bend around certain things and achieve more flexibility. Okay. So radio waves are the easiest example when it comes to that. So radio waves have a very long wavelength, which makes them bendy and stretchy. Think of them like rubber or clay, where they're malleable. Okay, and that's useful. We use radios to communicate, right? So in your car, when you turn on the radio, your car has an antenna. That antenna is picking up radio waves from the radio station. The radio station is nowhere near your car. Okay, the radio station is somewhere very, very far away, but somehow the wave still reaches your car. And the only reason they can do that is because radio waves are able to bend around buildings and things like that. Think about where it has to travel to. Think about a city like New York. New York has skyscrapers and tall buildings everywhere. If radio waves didn't have the ability to bend around the buildings and things like that, radios wouldn't work. Okay, so that's what it means to behave like a wave. Okay, so now we're going to go through specifically the different types of waves. Okay, so remember, more energies to the right, less energies to the left. So in order of increasing energy, radio is the weakest, then you have micro, then you have infrared, then you have visible. Visible, as the name implies, is what we can see. Then you have ultraviolet. This is what you wear sunglasses to protect your eyes from. It's also what you wear sunscreen for. You have to protect yourself from the ultraviolet rays. Then you have X-rays, and then you have gamma rays. Okay, and we'll get through each of them. We're going to go through each of them now. So radio waves are the weakest wave. They have the least amount of energy, and they have the longest wavelength. Okay, so think of wavelength as determining the bendability. The longer the wavelength, the easier it is to bend around corners. Okay, so radio waves have the longest wavelength. They're often used in communication because they can travel really far without getting disrupted. And they're used to detect certain things in outer space because certain things absorb them. So if they send it out and they don't get it back, then they know something's there. Okay, they use it to communicate from really far away with satellites and things like that because it can travel really far without getting disrupted. Right? So that's what radio waves. Then you have microwaves. Microwaves are also used in communication. Their wavelength is a little shorter than radio waves, so they can't travel as far, but they do have more energy, which means they can transmit more information. Okay, so they use them in satellites. So notice how for radio, it's talking about deep space. Okay, so really, really far away. But we can still use the microwaves for satellites that are just within our orbit. They're a little closer, okay? And they're also used in your cell phones. You also use microwaves to heat up your food, okay? What it does is it causes vibrations in the molecules, and that vibration produces heat, and that's how you heat up your food. Okay, so that's microwaves. Then you have infrared. If you've ever seen those heat vision or thermal vision goggles, I'm sure you've seen them in video games or in movies or things like that. What they're looking at is infrared waves. That's what they detect. Infrared waves are not necessarily heat. Okay, so let me clear that up because what people get confused with is thermal vision goggles, they look at heat. What they're looking at is waves that are given off by already hot objects. Okay, so in order for something to emit a infrared wave, it needs to already be warm. So an infrared wave is a wave that's given off by anything that is warm, such as our bodies, heat lamps, things like that, anything that's hot. So it needs to already be hot in order to emit the wave. But what it's emitting, it's not emitting heat, because remember, infrared waves, it's light. It's emitting a light, but it's a type of light that only warm objects give off. So that is the difference. So what thermal vision goggles are looking for is these infrared waves. Okay, that's what it's looking at. And based off of the waves, it can give you a temperature, but it's not looking at heat. It's looking at these waves. That's the difference. And some animals or insects can see these waves, and that's how they decide, where they want to bite you at. Like mosquitoes. Mosquitoes can see them. Then you have visible light. Visible light, as the name implies, is what we can see. If you look at the band, it is a very small window, okay? Only a very small portion of light falls under visible light that we can see, okay? And those your yellows, your blues, your violets, that is what the visible light spectrum is. Then you have ultraviolet. This is what causes sunburns, and this is what is absorbed by the ozone layer. So all those years when people were talking about the ozone layers being destroyed or depleted, that was a concern because without the ozone layer, you get more UV light coming through. And if you get more UV light coming through, you get more sunburn, and not just sunburn. UV light can also cause skin cancer. Okay, so you get skin cancer and things like that. Here they're saying to use it for sterilization. I'm sure you guys have all heard of something called a black light. A black light is just UV light. It's something that we use to sanitize things. So in the classroom, where the goggles are, there's a black light in there. So before labs, I turn on the black light. The black light kills the bacteria and it disinfects the goggles. Okay. So when they say they use it for sterilization, that's what they're talking about. They're talking about something called the black light. Then you have X-rays. X-rays are used for bone to see your skeletal structure, and the reason that's the case is because of this. Okay, soft tissue is transparent to X-rays, so only your bones and things like that can absorb them. So they're solid, which is why in the X-ray, the images you see the skeletal structure because the bones absorb them. That doesn't let them pass them through, but the rest, the X-rays just go straight through it. Okay, the soft tissue. Now we're getting on the high energy stuff, and this is the stuff that starts to act like particles. Okay, so I would say from after visible, these things start to behave more like particles. They're more direct. Okay, and that's important for this next component, the gamma rays. We use them in fighting cancer. Okay, the reason we can do this is because they are very high energy, and because they're very high energy, we can aim them, okay? We can control where we want them to affect the body, okay? We call that targeted radiation, okay? So when we're talking about cancer, there's multiple things you can do, okay? Radiation treatment is one of them. Okay, radiation treatment is getting better. What it does is it focuses on a specific point. So if they know the cancer cells are in this location, rather than doing something like chemo is a full body thing. It's exposing the entire body to this chemical versus targeted radiation focuses on a specific spot. Okay, targeted radiation is better because it doesn't damage the entire body. Okay, but we can only do this because it's high energy and behaves like a particle. We can aim it, we can shoot it. Okay, things like radio waves and microwaves, they're more what's it called? Broad target. So it's like a buckshot, if you know what a buckshot is. A buckshot is a shotgun shell that shoots pellets, okay? So it's like a bunch of pellets going out. It hits multiple things. So think of the radio waves and the microwaves as those pellets. It shoots them out and it hits multiple targets. Gamma rays and X rays are a single slug, okay? It's only one single particle that you aim and can control. Okay, so that's what when they talk about behaving more like a wave and more like a particle, that's what they're referring to. Okay, so that covers all of the different EM waves, the different types of light: radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. And there's one more piece that I want to discuss. This section doesn't give us the light equation, but that is something I want to talk about. Okay. So all EM waves travel at the speed of light, okay? All EM waves travel at the speed of light. This is a big highlight. So how do we know which type of wave we get? We base that off the wavelength and frequency, but how do we calculate those things? It's with the following equation. So I need a blank sheet. There really is no blank sheet. I'm going to write it out here. I have it here. I'm going to write it out. So the speed of light is written as c. Okay, so c, speed of light is c. Okay, and this is one of the worksheets we're going to be doing today. The speed of light is equal to the wavelength, okay, of something times its frequency, which is always equal to 3 times 10 to the 8 meters per second. Okay, meters per second. So light travels basically 300 million meters in a second. Okay, so light travels really, really fast. Okay, so when you turn on a switch, it looks like the whole room gets filled up with light instantly. That's because of how fast light can travel. Okay, so this is the speed of light. The knobs, think of wavelength and frequency as knobs that you can turn. Okay, so if you turn up frequency, you need to turn down wavelength. Okay, and that's seen in the diagram. That's seen in the diagram. So look at the different bars that you see here, at the top, at the bottom. Going to the right, I said you get more energy. But what also happens to wavelength? Going to the right, wavelength gets shorter. Okay, notice how the further right you get, it gets shorter. So here we have 10 to the negative 1, negative 2, negative 3, and it goes all the way down to negative 10, negative 11, negative 12. So as the waves get stronger, wavelength gets shorter, but frequency gets higher. Okay, but they all travel at the same speed, and you can see that in the equation. So if we turn up frequency, so if we make frequency higher, we have to make the wavelength shorter, according to this equation, in order to keep the speed of light the same. Okay, so when you turn one up, the other one has to come down. And now I specifically mentioned this in a vacuum. So the speed of light is the same, assuming we are talking about the same medium. The medium is what something travels through. So light travels through air, so the air would be the medium in that case. But the reason speed of light isn't the same, I can give you an example now with water. If you've ever put a straw in water at an angle, you can see that the entry point isn't the same as it is in like the water image. And let's see if I can Google let me see, straw in water. Let's see if I can show you exactly what I mean. Yeah, boom, exactly. So here's exactly what I mean. So when you put a straw in water, notice how where it appears it enters at the top, it like gets cut off and it bends. The reason for that is because the speed of light is not the same in air and in water. So once you start to go to different surfaces, or not surfaces, once you start to go to different mediums, it changes things. So the speed of light is not the same in water as it is in air, as it is in a vacuum. So it changes because it has to travel through stuff. So that's what I wanted to highlight. Okay, that's what I wanted to highlight. And I'm gonna. This is the just speed of light is equal to wavelength times frequency, and you're gonna use that to answer some questions. Okay. So if you knew what the frequency was, if I told you here's the frequency of a light, what's the wavelength, you can calculate that using that equation. Okay. I'm going to demonstrate that in a second. Okay. So that's it for the presentation. Now it's just utilizing that one mathematical formula. And what you have is a study guide to do today. The study guide just focuses on the conceptual pieces, everything we've talked about. And then I added this. I wanted to add this just to give you some mathematical practice. Okay. It's just this one simple equation. You may be asked to find frequency, you may be asked to find wavelength, and then you have to rearrange the equation. For the study guide, so the questions, number one, what does the figure above represent? It's asking you, what is this? Okay, what is this? What does this represent? Number two says place the term high energy and low energy on the correct sides. So which side has the increasing energy? We talked about that. I'll let you fill that in. Number three says identify the type of relationship. I want to go through the questions to make sure there's no confusion. How are we doing on time? Okay, cool. Identify the type of relationship between wavelength and frequency, wavelength and energy, and frequency and energy. So what they're basically asking you is, as one goes up, what happens to the other? So if we look at wavelength and frequency, what they're asking is, as wavelength increases or decreases, what happens to the frequency? So for example, let me see, I'm cutting off something here. Let me not do that. Going to the right, wavelength is getting shorter. As wavelength gets shorter, what happens to the frequency? You can look at either direction. Going to the left, it gets longer. As it gets longer, what happens to the frequency? Okay, that's what they mean. If you look at wavelength and energy, well, you have to remember in what direction is energy increasing. Okay, so once you know what direction energy is increasing, you can say as wavelength gets shorter or as wavelength gets longer, what happens to your energy? And then same thing with frequency. As frequency increases or decreases, what happens to that energy? That's what they're asking you for when they say relationship. As one goes up, what happens to the other one? Okay, that's what they're asking you for. And then number four says give a practical application of each type of radiation. Basically, what are they used for? X-rays. They're used in hospitals to check for bone fractures. Okay, you know that you've seen that one before. Some of you may have broken something before and had to get that done. Ultraviolet. We use them in black lights to sanitize things. So that's what they're asking you for. Give an application. What is one way you can use these things in real life? Okay. And now I'm going to demonstrate how to use this equation here. Okay, speed of light is equal to wavelength times frequency, which is equal to this number in a vacuum. So if you see in a vacuum, so number one, number two says travels in a vacuum. And they're asking you to find frequency and wavelength. You already know the speed, and you know one of these, you can rearrange the equation and solve for the other. And I'll do one of those, okay? But if it doesn't say it's in a vacuum, then they'll give you the speed. So here that says the speed of light in water is this. If you know the frequency or one or the other, what is the other one? And vice versa, okay? So if it's in a vacuum, this is the number you're using. If it's not, then they'll give you that information, okay? So now let's go through one of the problems. I'll just do number one. I'll just do number one because the rest of them are going to follow the same pattern. So again, C is equal to W times F. What are we looking for? We are looking for the frequency. Remember, I always tell you to look at the final destination first. We are looking for frequency. Right now, my equation is not set up to give me frequency. I need to get frequency by itself. So I have C is equal to W times F. I need to get rid of the W. To get rid of something, you need to do the opposite. Right now, we're multiplying by W, so to get rid of it, we need to divide. If you do that, you get that frequency is equal to the speed of light, which is C, divided by W. Okay, so F is equal to C, divide both sides by W. So now that we have our equation set up, we can plug in the numbers. We want to know what is the frequency if the wavelength is this value, 4 times 10 to the 7. Let's plug our numbers in. What is C? C is the speed of light. We're traveling in a vacuum, so we know what the speed of light is already. It would be 3 times 10 to the 8th. And then we need to divide that by 4 times 10 to the negative 7. Okay? If you plug that into your calculator, you get that frequency is equal to, let me plug that in now, 3 times 10 to the 8th divided by 4 times 10 to the power of negative 7. And you get 7.5 times 10 to the 14. Okay? The unit of frequency is hertz. Okay? Hz, which you may have seen on your radios before. That's something I should probably look at real quick. Okay? So wavelength, it's a length, so it's in meters. Okay? But frequency is in hertz, Hz. All that means it's a time value. Okay? It's a time value. But just know the unit of frequency is in hertz. So for number 2, you see it says Hz, 3 is Hz. That Hz, that's the frequency value. That is the unit of frequency. Okay, so wavelength is in meters, frequency is in hertz, Hz. Okay, so this is our frequency. F is equal to 7.5 times 10 to the 14. That is our answer for number 1. If I asked you what type of light is that, you would just look at the diagram. Where is 10 to the 14? 10 to the 14 is here. It's 7.5 times 10 to the 14, so it would be more in here. And you just look at that, and it would fall under infrared. Okay, so this would be infrared light. Okay, and that's how you use that equation. For number 2, you're being asked to find wavelength instead of frequency. So instead of solving for F, solve for W. And number 3, you're being asked to find wavelength again, so do the same thing. And then number 4, you're asked to find speed. So you would just leave the equation alone because it's already set up to find speed. Okay. So that's it for today, and that'll be it for the electromagnetic spectrum unit. So after today, we're gonna have an assessment tomorrow, and then we're gonna start a new unit. Okay. So that's it for this unit. If you have any questions, as always, please reach out. Please reach out, guys. If you don't reach out, then I can't assist. Okay. Email me if you have any questions, and I will do my best to answer them. But if you don't send me anything, then I can't help you. But that's it for today, guys. I wish you all the best. Happy Tuesday. Take care and enjoy the rest of your day.